Hello and welcome to The Explainer. If you've ever worked with a really big data set in Python, you've probably had that feeling, like you're just watching paint dry. Well, today we're diving into NumPy. It's kind of the secret weapon that makes Python blazingly fast for data science. So let's get right into it.
Okay, so before we can really appreciate the solution, we got to understand the problem, right? And that problem, it starts with something every single Python programmer knows and loves: the list. I mean, lists are great. They're super flexible. But as we're about to see, that flexibility, it comes at a pretty steep price, especially when you start dealing with huge amounts of data.
So let's say you want to multiply two giant lists of numbers. Your first instinct is probably to reach for a for loop. And look, that works, but it is slow. And why is that? Well, because Python lists are so flexible, the computer has to do a ton of extra work behind the scenes for every single item. It's got to check its type, figure out where it is in memory, and all that overhead, it just adds up really, really fast. Just look at the difference here. On the left, you've got the standard Python way. You're writing an explicit loop, going through each item one by one. It's not just slow, it's kind of clunky to write. But then you look at the right. That's the NumPy way. It's clean, it's simple, it's just elegant. It looks exactly like the math you'd write on a piece of paper. And like we're about to see, it is ridiculously fast. Writing elegant code is a nice bonus for sure, but it's not the main event. The real reason data scientists build their entire workflows around NumPy, well, it's all about speed. We're talking about a truly massive performance boost.
Okay, get this. For a list with, say, 1 million numbers, NumPy can be up to 50 times faster. Yeah, 50. That's the difference between going to make a full pot of coffee while your code runs and getting your result pretty much instantly. So, the huge question is, how on earth does it do that?
Well, the secret sauce is really all about NumPy's core data structure. It's called the ND array, which is just short for n-dimensional array. Now, unlike a super flexible Python list, an ND array plays by some very, very strict rules. And it's exactly those rules that unlock this kind of incredible performance.
I absolutely love this analogy, because it really gets to the heart of the matter. Think of a Python list like a big, floppy shopping bag. You can just toss anything you want in there, right? An apple, a book, your keys, whatever. But a NumPy array, that's more like a custom-engineered cargo container. It's optimized to hold only one type of item. And that specialization, that's precisely where all its power comes from.
So let's break this down. The key thing to see here is that NumPy arrays are fast because they have one big rule. All the elements have to be the exact same type. They're what we call homogeneous. Because of this rule, NumPy can store all that data in one continuous block of memory, which is way more efficient. And since it knows every element is the same, it doesn't have to use slow Python to check things. Instead, it can unleash these highly optimized precompiled C functions to run operations on the entire array all at once. So we get to say goodbye to those slow one-by-one Python loops. Okay, so this all sounds great in theory, but how do you actually do it? Let's talk about building your very first array. And the good news is, if you already know some Python, creating a NumPy array is super simple. You've got a few really powerful ways to get started. Probably the most common way is to just take a Python list you already have and wrap it in the np.array function. That's it. NumPy takes care of all the hard work, transforming it into that powerful, efficient ND array structure for you. But what if you don't have a list to start with? What then? Well, you could use np.arranging. This lets you create an array with a whole range of evenly spaced values. It works almost exactly like Python's built-in range function, but instead of giving you back a list iterator, it hands you a ready-to-go NumPy array. Another really handy thing you can do is build a kind of empty slate. Functions like np.zeros let you create an array of a specific shape, say a 2x3 matrix, and it'll just fill it with placeholders, in this case zeros. This is super useful when you know the size of the data you're going to have, but you don't actually have the values to put in there yet. All right, so you've built your array. The next step, obviously, is to start playing with it. This is where we get into the fun stuff, shaping it, slicing it, and basically conquering our data. And this is where you really start to feel that NumPy power. Every single NumPy array has a .shape attribute. It's just a quick way to see its dimensions. So here we can see the shape is 3, 3, which just means it has 3 rows and 3 columns. What's really cool is you can even change that shape on the fly with the dot reshape method. You can turn a flat one-dimensional array into, say, a two-dimensional matrix, just as long as the total number of elements stays the same.
Okay, but listen up, because this next part is critical, especially for beginners. This is something that trips up almost everyone at some point. When you slice a NumPy array, you are not getting a new, independent copy of the data. What you're getting is something called a view into the original array.
So watch this happen. First, we create our array, let's call it A. Then, we create B just by taking a slice of A. Now here's the kicker. We change the first element of our slice, B, to the number 99. But when we go back and look at the original array, A, whoa, it has changed too. See? That's because B isn't a copy, it's just a view. Think of it like a window looking into A's data. Now this is done on purpose for memory efficiency, so you're not making pointless copies of huge arrays. But you have to be aware of it. If you actually want a brand new, independent copy, you have to be explicit and ask for it with the .copy method.
So we've established that NumPy is fast, like really fast. But now let's pull back the curtain and see the real magic behind it. It really all boils down to two incredibly powerful and kind of related concepts: vectorization and broadcasting. First up, we have vectorization. And honestly, it's a fancy word for a simple idea. You can perform an operation on the entire array all at once without you having to write a Python for loop. Now, the looping still happens, don't get me wrong, but it's all done behind the scenes in that super fast optimized C code, not in slow and steady Python. And the second ingredient in this magic potion is broadcasting. This is where NumPy gets really clever. It's the term for how NumPy can handle operations between arrays that have different but still compatible shapes. What it does is it essentially stretches or broadcasts the smaller array across the larger one so the math works out.
Here's a super simple example. Let's say you add a single number, a scalar, as it's called, to an entire array. You don't have to write a loop to do that. NumPy is smart enough to understand, oh, you want to add that number to every single element in this array? So it just broadcasts that 5 across the whole array, and bam, the addition is done. Almost instantly.
And to make this even more real, here's a perfect example of this in action. At its core, what is a digital image? It's really just a giant NumPy array. That's all it is. Each number inside that array is just a value that represents a single pixel's color or brightness.
So think about it. If you want to make an entire image brighter, you don't have to write some crazy loop to go through every single one of the thousands or even millions of pixels. Nope. You just take your image array and you add a number to it. That's it. NumPy broadcasts that addition across the entire array, and just like that, a brighter image. That is the incredible, practical power of NumPy in action.
So when you put all of these pieces together, you've basically unlocked a new superpower for programming in Python. So let's do a quick recap of the most important things to remember.
All right, so here's what it all boils down to. First, the ND array, that's your new best friend for any kind of numerical data. Second, the magic behind its speed comes from vectorization and broadcasting, which lets you write simple code that runs incredibly fast. And finally, the one big gotcha to always watch out for. Slicing creates a view, not a copy. Don't forget that one.
And now that you've got these fundamentals down, the possibilities are just wide open. We're talking data science, machine learning, scientific research. It's everywhere. From now on, anytime you find yourself working with large sets of numbers in Python, I want you to think NumPy. You've just unlocked a genuine superpower for your programming toolkit. Where are you going to go build with it?